Now, I've been doing some projects recently working with digital filters on FPGAs, and it got me thinking, what would be the best filter you could get if you dedicated all of the resources on an FPGA just to that one function, just to that digital filter? How good a filter could you make, and what performance could you get? So that's what I'm going to look at today. So the actual board I have is the Cyclone V starter kit, which is an FPGA development board made by Thoracic. And this has a Cyclone V FPGA on board. Pretty mid-range kind of FPGA, but reasonable performance. And I also have a daughter board here, and this has a pair of 65 megasample per second A to D converters, and also a pair of 125 megasample per second DACs. So this is the hardware I'll be using for the experiment today. Now, we all know you can make analog filters out of inductors, capacitors, and resistors, but digital filters, you can actually make them out of three main things too. So you need your delay element, your multipliers, and your adders. And if you combine these in the right way, you can make a digital filter with an arbitrary cutoff, roll off, and all the same kinds of properties that you get with analog filters. So for a finite impulse response filter, which is the one I'll be using today, the process of designing the filter is normally specifying first what cutoff you want, some of the other properties of the filter, and then trying to find the coefficient values, that's the multiplier values, that would give you the filter that you want. The other important thing is the number of coefficients that you have, and basically that means the number of stages that you have in the filter. Now, the more stages you have in the filter, the better the performance, the steeper the roll-off, and basically the filter will perform much better. But of course, that comes at a cost of extra hardware resources on your device. So I've written a MATLAB script here which computes the filter coefficients for 7 different types of filter, and each filter has a different number of coefficients. Okay, so we start off with a rather modest filter with only 20 coefficients, and we slowly build our way up to a monster of a filter really, which has 350 coefficients. And we expect to see a big difference in performance here. And the more coefficients we have, the closer we should see the approximation to a brick wall filter, where you go from the pass band to the stop band without any transition. Now, all of these filters are low pass filters, and they all have cutoff frequency of 0.2 times the sampling frequency. So if the sampling frequency is 100 megahertz, then the cutoff in this case would be 20 megahertz. Now later on, I'll be using a sampling frequency of 50 megahertz, and this means we should have a cutoff frequency of 10 megahertz. So let's go ahead and see what the performance of these filters are like based on MATLAB simulations. And as you can see, as the number of coefficients increases, we begin to approximate a brick wall filter more and more. So the next question is, how do we take these coefficient values and implement them on the FPGA? So let's open up Quartus and take a look. So here I am in Quartus, and you can see already I have made a block diagram schematic file. I have input pins here coming from my A to D converter. This is A to D converter A on the daughter board. This is the clock, so I have a 50 megahertz clock coming in to this module here, and then I have the output pins, so it's a 14-bit DAC. We're using DAC B on the board here, and these are the output pins. You have to be careful that you get those pins right. Now we also have some outputs from the module here, which are just control signals to the A to D converter and DAC. Now, within this module, I have the instantiation of the FIR filter itself, and the next thing I'll show you now is the FIR mega function, which I'm using to implement this filter. But what I've done next is actually export my coefficients from MATLAB, from within the MATLAB workspace to Notepad. And then you can import those coefficients into the FIR mega function from a .text file. So I'm going to start off with the 20th order filter first. So I'm just going to copy and paste these and just save as filt20.filt20. So now within Quartus, I can create a new FIR filter. I'll call this one FIR20. And now we can go through the Mega Wizard and hopefully import our coefficients that we just made in MATLAB. So we'll have a look at how we can do this now. So this is the Mega Wizard for the FIR filter. We'll just change these to 50 because we know that we have a 50 megahertz clock. But now we can go to coefficients and we can select import from file and we can do a search for filt20. So these are the ones that we just copied and pasted into the text file. We can just see if these load up. So there we go. So, you know, we can go back and compare this to the frequency response that we saw from the MATLAB simulation. But this is basically our 20th order FIR filter. And you can see it doesn't perform very well. You can see this is an awful transition period. It takes an absolute age before you reach the, before you get down to 30, 40 decibels of attenuation. And we can definitely improve on this. But just as a starting point, this is the first one we'll put onto the FPGA. And you can see we have a 14-bit input width. We're choosing signed binary as the input type. And for the output, now the output width is 27 bits because you do get bit growth as the signal propagates through the filter because you have all those multipliers and adders. So you have to make a judgment if you want to truncate that signal back down to 14 bits. And what I'm choosing to do here is remove the 12 least significant bits and remove one most significant bit. Now there might be some trial and error here to see whether that gives us a signal which is fully visible. We'll have to wait and see about that. And there we go. We've just created the FIR filter and now it appears in IP components of the Project Navigator. So now we can instantiate this into our design. So to instantiate this filter, I'll just overwrite the existing filter that I have here. So will be FIR20, which will match the entity name in the IP catalog. And then for the next one, the instantiation name, well, we can just keep that the same. We can choose whichever instantiation name that we want. Now everything else matches out within this module. We have a 14-bit signal coming in and a 14-bit signal coming out. So I think we can go ahead and compile this design. But before we look at the compilation results, and this is for people still playing along at home, this is the experimental setup that I'm using today. So we have a signal generator, and that's passing a signal into the A to D converter, the AD9248, which is a 14-bit A to D converter. Then we have the FPGA, and the FIR filter is implemented within the FPGA, and then the output signal will be turned into an analog signal using the 14-bit DAC, and then we'll have a look at that signal on the oscilloscope. And what we'll also do is compare it with the original signal. So we'll also loop a signal from the signal generator into the oscilloscope. So this is the experimental setup. So we have our first compilation result here. This is for the 20th order FIR filter, and you can see it's not really using much of the resources on this FPGA. We're only using, well, less than 1% of the logic elements on this chip, and we're also using only 6 of the DSP blocks. And I think the DSP blocks will be quite important with the implementation of this filter, but we're only using 6 out of 150 DSP blocks. So far, we're only using a tiny fraction of the resources of this FPGA. But anyway, let's implement this and let's check to see if it is behaving as we expect. So I'm at the bench here, and you can see this is the FPGA development board. This is my daughter board with the A to D converter and DAC. The signal going into the
A to D converter is coming from this signal generator here. So that's looping into the A to D converter. It's going into the FPGA. It's being filtered. It's coming back out through the DAC, and then it's going up to my oscilloscope here. And I've got the two signals going into the oscilloscope. I've got the original signal from the signal generator and also the filtered signal from the FPGA. And the blue line here, channel 2, is the original signal, so we don't expect that to change. But the yellow one, that is the filtered signal. So as we increase the frequency, we should start to see that diminish in amplitude. At the moment, I'm on 1 megahertz, and we're measuring about 24 millivolts on the filtered signal. Now, as I said before, the actual range of that signal will be affected by our choice of bits that we chose to keep, because there's bit growth through the filter, so we have to decide if we discard most significant bits or least significant bits. So that doesn't really matter. As long as you can see the full range of the signal there, that's okay. Now, we're reading 24 millivolts. I just want to verify that the 6 dB cutoff happens at the cutoff frequency, which should be 5 megahertz. So I'm going to change this to 5 megahertz. Now, we were on 24, so just move that up, and you can see now this is at 5 megahertz, and you can see the amplitude of the signal is halved. So that's a pretty good indication that this filter is behaving as we expect. We can carry on increasing, and you can see the signal will very quickly die away. That's at 10 megahertz now. But this isn't a very good filter, is it? Because even significantly below, this is at 3 megahertz, and you can see the signal is already attenuated. This is at 4 megahertz, and you can see we've already got a good few dBs off the amplitude of the signal, even a good 1 megahertz before the cutoff frequency. So this isn't a very good filter. We can really improve on this if we wanted. So let's go back to Quartus and see if we can make a better filter. Another way to visualize this is to do a frequency sweep. You can see I've got a frequency sweep starting from 1 megahertz going up to 10 megahertz in 300 milliseconds. And if you do that kind of frequency sweep, then that really gives you the actual shape of the filter. And you can see we've got a very slow cutoff, a very slow roll off. And again, we can improve on this.
So I think it's time to increase the order of this filter. So what I'm going to do is go back to MATLAB. I'm going to go for 100, a 100th order filter. So I'm just going to copy and paste these coefficients into my text file, and I'm going to save this as filt 100. And then I'm going to go back to Quartus, and I'm going to create another FIR filter, and I'm going to import these coefficients. If I call this FIR 100, and then I'm going to import these coefficients, and hopefully that should give us a 100th order. So as you can see, this is the 100th order filter. Now I've got 100 coefficients. It's already looking a lot better here. It's looking more like a brick wall. Now with the input and output options, I'm choosing now to remove 5 most significant bits and 10 least significant bits, because the previous filter, our sort of magnitude level was quite low. So if we remove fewer most significant bits, maybe we can increase the level without saturating the bits that we have. Let's have a look how this one goes. So we have the compilation result for the 100th order filter. We've used 26 DSP blocks and less than 1% of the logic elements. So it's creeping up, but still a tiny fraction of the resources of the chip.
So I've programmed the FPGA, and we can take a look at the performance of the 100th order filter. And it's clear to see here now that the performance is much better than the 20th order filter. Much sharper cutoff, much better performance in general. Take a look at how much further we can go with this.
Now you can see I've gone for a 350th order filter, and I've tried to compile this and we've hit our first roadblock here. You can see it hasn't compiled. It's hit the limit of the resources on the chip. And you can see the problem is the number of DSP blocks that we have available. So we need 156 DSP blocks. And we've exceeded the capacity, which is 150 on the FPGA that I have. There could be a way to trade off the use of DSP blocks against just general purpose logic elements. And I've had to play around with the implementation options here, but I haven't managed to make the compiler use logic elements rather than the DSP blocks. If anyone knows how to do this, please let me know. But for now, I think we'll have to go to a lower number of coefficients. Okay, so the compilation for the 320th order filter has finished and it's compiled successfully, so it does fit on this FPGA. I'm not quite sure why this is only using 81 DSP blocks, and it's also using more logic elements, so I'm not quite sure what it's doing in terms of the balance of those resources being used. But anyway, let's go and check the performance of this filter.
So this is the 320th order filter. You can see it's starting to look quite impressive. Look at the steepness of transition. So very, very sharp transition. So I'm pleased with this. I'm not sure if we can push this any further, but I was quite interested in the way the compiler was trading off the logic elements with the DSP blocks there. So I'm sure there's more we could do if we were willing to spend the time to try to get that balance right.
And it's always interesting to have a look at the RTL viewer to see how the compiler has arranged the design and what kind of complexity we have. So I'm going to go into tools, and I'm going to go into netlist viewers, RTL viewer, and this is the way at the register level. This is the way that the software is decided to lay out the design. So we can see this is the top level, but we can keep on clicking through and we can get an idea for the kind of complexity we have here. So let's have a look into that one. Well, that's not too bad. Let's have a look into this one. So this is the kind of complexity we're talking about with this kind of filter. This is the 320th order filter. Now, of course, this is going to be made out of a sequence of like a chain of parts of the filter arranged as a chain. So, but we can still see the kind of complexity we're dealing with here. So I just thought that would be an interesting thing to look. So in summary, we managed to get up to a 320th order FIR digital filter. Now, of course, if you have a different device, different resources on the chip, then you'll be able to develop maybe a better filter than I have with my particular FPGA. And I'm sure as well, I'm quite curious about the way the compiler has traded off the use of the DSP blocks, which I guess are the preferred way to build a digital filter because it gives you those hardware multipliers, versus the logic elements. So I'm sure if we tweaked balance between those two resources, we could probably get the order of the filter up to a much higher order. But anyway, I thought that was a really interesting experiment. If you have any advice or tips on how to get a better filter, then please let me know. I think I'll finish it there. So thank you very much for watching.